Hello everyone, welcome back to ptet.chemistry channel. So my name is Mr. On, and in this tutorial video I'll cover another qualitative analysis experimental video. In my other video I've talked about water of crystallization that is present in a lot of ionic compounds where the water molecules actually crystallize, or they co-crystallize. They crystallize together within the giant ionic structure framework, such that we get hydrated ionic compounds. Therefore, we have water of crystallization that we could evaporate off when we heat it strongly in a test tube or in a boiling tube, and we will see colorless liquid at the upper part of the tube where the water vapor or the steam would have condensed. You saw a colorless liquid on the upper part of the tube. It indicates there's water being given off. It indicates there is water crystallization in the compound, in the original compound. And of course, if your original compound was colored, then you need to think about, is there a color change? Has there been a color change from what you started to what you end up with? But if your original compound was white, then there isn't really much you can talk about, apart from commenting on the appearance of the solid as well as what else you see. That's the whole idea about qualitative analysis, is to think about what do you see, what do you observe, okay, all your five senses. In today's tutorial video, I will specifically talk on another aspect of qualitative analysis. So behind me, I've got actually a lot of chemicals that I found in our storage. So a lot of these chemicals, they are no longer applicable, or they are no longer commonly tested or assessed in O-level or IGCSE practical, and they have been moved over to the more advanced A-level kind of practical setting. However, never say never, because Cambridge is very innovative. They are trying to mix and match a lot of the A-level practical stuff and move it into the O-level practical stuff, because since it is just practical study, since it's just doing experiments, it's less about knowledge, it's about the skills, the experimental skills in terms of observation and the ability to conclude or to deduce from your observations what you can say the cations or the anions present. Okay, so I have specifically here, this is a compound, it's a hydrated compound, so it's called aluminium ammonium sulfate. So it is actually a mixture. So if you see the formula there is that, okay. So what I'll do is I will screencast on my iPad screen at the same time. Okay, so you already had a look at that. So what happened then is, actually the whole tub feels a bit wet because of the water crystallization that has come off. So you have aluminium, which is aluminium 3+. You have ammonium, which is NH4+. And then what you have is you have sulfate, which is SO4 2-. Because you have a 3+ and NH4+, altogether that is +3 +1, they give you +4. So you need a -4, which is equal to -2 × 2. So you need 2 sulfate. Turns out that this is a compound which is hydrated, similar to what I talked to you in the other tutorial video. This is .12H2O. So there's 12 water molecules of crystallization. Essentially what this is then is, this is a mixture, by the way. This is a mixture because you can imagine it as being, what can you imagine this one being? Usually you would think, well, it's not exactly a mixture, because if it is a mixture, you have Al3+ and 2 SO4 2-, 3 of it like that, and then you will have NH4+, 2 of them, and SO4 2-. As you can see on the screen, that I will have it a picture by picture there. So as a mixture, you would have that, but then if you add them up together, then you have 2 of the 3+, 2 of the NH4+, and 4 of the SO4 2-. 2:2:4. Then you can simplify it to give you the simplest ratio of 1:1:2. And guess what? That means you have 1 Al3+, just like this thing here, 1 Al3+, 1 NH4+, and 2 SO4 2-. So I was right, this is a mixture. It's just that the number doesn't look so good when you add them up, because they do simplify to give you the simplest ratio, and that is the whole idea of a chemical formula, is to get the simplest ratio of each of the species present. In this case, these are the ions. So this is a mixture of two different salts. One is aluminum sulfate, the other one is ammonium sulfate. So it is white in color. The top is looking a bit disgusting, but I'll just show you very quickly. It is white in powder, so it is solid, okay, but the top is pretty wet on the outside, so there's probably just the water crystallization that has formed somehow. I mean, this was kept in the cabinet for a long time, and where I'm based in a very hot and humid country, Brunei, so a lot of the chemicals, they are not at room temperature anymore. Okay, the other one I want to talk about today is this thing called ammonium iron 2 sulfate. So I might have talked about this in my other tutorial video on water crystallization, but that is not my focus today. If you look carefully, there are two cations. There is NH4+, and this says iron bracket 2, the Roman numeral. That means the oxidation state of the iron is actually iron 2+, or iron plus 2. So on the screen here you will see I have got Fe2+, and then I've got sulfate. They also put down pure there. I don't know if you can see it. Chem pure. Alright, okay. So SO4 2-. Again, we know the charges of the ions, okay, and in terms of to balancing the charges, you will need, I think, two of the ammonium. As you can see, these are the formula: 2 of the ammonium, 1 of the iron 2, and because you have +1 times 2, then you have 1 time +2, that give you +4, and that charge will be balanced out by -2 times 2, which is -4. So the overall compound has no charge at all. There's also a thing given there, which is, I don't know if they give you, molecular weight. The one at the bottom right hand side there, you see around 300 and something. So I'm just going to show you using my very primitive periodic table. I'm just going to go grab it. So this is the lab that I used to teach in my current school. So my current level of teaching is O level. So these are the periodic table that are a bit primitive. They use the relative atomic mass only to the nearest whole number. So what can we say? There is 1 nitrogen there, so 1 times 14. There is 4 hydrogen, so 4 times 1. And then the whole thing has to be bracketed twice, because I have 2 times NH4+, I have 1 iron 2+, so iron has a relative atomic mass of 56. The reason we can just use 56, which is the relative atomic mass for iron, rather than iron 2+, is because iron going to iron 2+ is a loss of 2 electrons, and electrons has a very negligible mass compared to protons and neutrons as part of the atomic structure. Remember, 1 electron is only about 2,000 times lighter than the mass of a proton or neutron. So being a 2+, you have lost 2 electrons, so what? Your mass is not going to change very much. Electrons are so much lighter. And then I have 2 times, because 2 sulfate, 1 times 32 plus 4 times 16. Oops. So these are just your usual exercise of calculating the relative molecular mass of this compound called ammonium iron 2 sulfate. Ammonium iron 2 sulfate. And look carefully, this is a 6-hydrate, so this is a hexahydrate, so it is .6H2O. The .6H2O means there's 6 water crystallization, so I need to add, I do not multiply, I add another 6 of water molecules, so 1 times 2 for the 2 hydrogen, and then 1 times 16. Okay, and you do all that on your calculator, which I forgot to bring my calculator. Anyway, I won't be doing a lot of calculations, so I'll just be using my phone. In fact, this is the only molar mass calculation I'll show you, just to recap what we have done in the other tutorial videos on the water crystallization stuff. Okay, so I want to focus more on qualitative analysis in this video actually, so let me just quickly get this done. 14 plus 4 is 18. 18 times 2 is 36 plus 56 plus 32 times 1 plus 16 times 4 is 96 times 2 is 192. And then I have 2 plus 16 is 18. 18 times 6 is 108. So a lot of the times workings are very important. If you just press everything into your calculator, you risk making a mistake. Okay, so I get 392. This is to the nearest whole number based on my periodic table from O-level IGCSE, which I use to do this calculation, and they're only to the nearest whole number. So as you could see here, the molecular weight, the molecular mass, the MR of this hexahydrate mixture of ammonium iron 2 sulfate is very close to this 392 whole number, which I calculated. This is a double salt, okay? These are usually what we call, so what we have again, right? What we have again is a double salt, just like the previous question. So it's ammonium, and then it's iron 2 plus, and then it's SO4 2 minus, 2 ammonium, 1 iron 2, and 2 of that. The water crystallization is not the important thing here. I want to highlight the thing there is called a double salt, where you know you have two different salt, which is ammonium sulfate and iron 2 sulfate mixed together. Just like in the previous example, I show you the ratios of the different ions mixed together. They get simplified, and as you can see from the screen in the previous question, we had the simplification of this ammonium sulfate, and it was white in color because these are not transition metal at all. They are from the main group, right? Group 3 metal. This is ammonium ions and ammonium salt, ammonium ions. They do not contain any transition metals or transition metal cations. Transition metals refer to this series there. So there is the big block of transition metals. You have done this in O-level or IGCSE, and you will carry it forward to A-level chemistry, where you deal with a lot more in depth into transition metal stuff in A2 chemistry. So there was iron 2 ammonium sulfate. There's another one. This is called, this bottle looks disgusting. It's a really old bottle. Not sure how clear it is, but I'll just move close to the screen. I hope you can see it's ammonium iron 3 sulfate, and it's also hydrated. They don't say it's hydrated, but look at the formula at the bottom. NH4 plus, Fe3 plus, okay? So plus 1 plus 3, so you only need 1 ammonium ion to balance out the plus, well, not to balance out, but to add to the plus 3. So plus 1 plus 3 will give you, okay, I better not hold this very long, so let me just move on with it. So this is ammonium iron 3. So ammonium iron 3 sulfate, and it is .12H2O. It is .12H2O. So the molecular weight is given there, the molecular mass, the MR is around 482.18. So you can do this as your own exercise based on what I show you in the previous example using ammonium iron 2 sulfate. The water crystallization again here means that they could ask you to heat this solid and take observations as qualitative analysis, and you will get colorless liquid form on the upper part of the tube. But also don't forget that, you know, it has a transition metal. It has iron 2 and iron 3 in the two different compounds, and therefore when you heat them and drive off the water crystallization, there might be a color change, as I'll show you later on in a little bit. Okay, so you have 1 ammonium and 1 iron 3, so plus 1 times 1 plus 3 times 1, you add them together, that's going to give you plus 4. What have I done here? Plus 3 times 1. Okay, and then that is going to give you minus 4 to balance out the charge there, and therefore you need 2 times minus 2, so you need 2 sulfate. So the formula of ammonium iron 3 sulfate is one of these, and 2 of these. Unlike the previous one, you have 2 ammonium and 1 Fe2 plus. Here you have 1 ammonium and 1 iron 3 plus. Okay, so the main difference here is Both of them contains ammonium sulfate, NH4+, SO4 2-, but you need 2 of the ammonium ion, okay, in that one formula unit. But don't forget that you have iron 2 versus iron 3. They are 2 different metal cations, and that's what this qualitative analysis is for, right? Ammonium iron 2 sulfate. So it doesn't look very clear from the bottle itself. It might look better when I scoop it out later on. Should be a little bit pale green, but it's got a lot of white solid because of the ammonium sulfate, so it might not look very clear. This is a very old sample. Don't know how old it is. It looks really whitish, and that is probably because of the color of the ammonium ion. Sorry, not the color of ammonium ions, the color of ammonium salts. Okay, so ammonium salts will be ionic. It has a giant ionic structure, so it's a solid at room temperature and pressure. But because it is not a giant ionic structure, they will predominantly, in fact, they will always be white in color, except when they are mixed with a transition metal compound, such as this double salt. Double salt is a mixture of 2 different salts. When you are mixed with a transition metal salt, a transition metal compound, you could become colored because of the mixture, right? Okay. Remember, mixture, 2 or more substances mixed together. You are not combining them, you are simply mixing them together. This is the idea of elements, compound, and mixture, as you have done in lower secondary and carry forward to your GCSE or IGCSE or even O-level and A-level chemistry. Okay. Enough on those 2 for the time being. The last 2 that I'm going to show you really is this thing that has come out in A-level chemistry. So in A-level chemistry, there's something called thermal decomposition. Okay. So in O-level, in IGCSE, you also learn thermal decomposition. So we know that group 2 carbonate can decompose. All right. So thermal decomposition. Group 2 carbonate. So group 2 carbonates decompose, and then group 2 hydroxide usually do not decompose. Okay, and if group 2 carbonate decompose and group 2 hydroxide do not decompose, guess what happened when you have another double salt? Well, they are not exactly double salt. This is what they call magnesium carbonate basic. Okay, they call it magnesium carbonate light here, but the other name is magnesium carbonate basic. All right. So magnesium carbonate basic, what does it mean? Magnesium carbonate is Mg2+, CO3 2-, such that you have MgCO3 1:1 ratio. So that is magnesium carbonate. Magnesium carbonate. And then you have magnesium hydroxide. Magnesium hydroxide is not very soluble in water at all. Okay, so magnesium hydroxide is Mg2+, OH- twice. Okay, so it's MgOH twice, and then when you mix them together, you're gonna get, in fact, this is how they are mixed together. This is the ratio at which they are mixed together. 3 of the MgCO3, so that means 3 of it mixed with 1 MgOH twice, and you have water crystallization. Here is 3H2O. So in terms of water crystallization here, so you have 3 of these, 1 of these, and 3 of these. So this dot does not mean multiply. It means if you work out the MR of MgCO3, if you work out the MR of MgCO3, you need to multiply the whole thing by 3, and then you add with the MR of this magnesium hydroxide, and then you add with 3 times the MR of H2O molecule, and then you will get, oh no, it doesn't have the molecular mass here. But anyway, you can work it out yourself, and that's essentially what could happen in an A-level paper. So it is a white solid, so it doesn't contain any transition metal complex at all. And the reason why this is interesting is because they can ask you in what we call gravimetric analysis. Gravimetric analysis is the A-level important concept, and this has also been asked in a O-level setting or IGCSE setting, but not as a practical, as an alternative to practical, because you can think about the experiments being like, let's say 3 MgCO3, MgOH twice, dot 3H2O. The first thing that will come off will be the water of crystallization. Remember, it's hydrated, so you will get colorless liquid form on the upper part of the tube, and hopefully I'll show you in a little bit and it will make more sense. And then what happened then is the magnesium carbonate is a group 2 carbonate. So group 2 carbonate become more difficult to decompose down group 2, but the earlier you are in the upper part of group 2, they decompose much easier. And these are things that will have been covered in the group 2 energetics in an A2 level. There's the second year of A levels. You actually are asked to explain why the group 2 carbonate become more stable to heat than group 2, and I think people who are doing A levels, you know where to find it in my topical playlist under A2 group 2 energetics. For those who are doing O-level IGCSE, the idea really is that in O-level IGCSE you are simply asked to remember, to state that the magnesium carbonate can decompose, calcium carbonate can decompose, but calcium carbonate takes more energy to decompose than magnesium carbonate. When they decompose, they will give you a group 2 oxide, so Mg2 plus O2 minus. That's why it's MgO, Mg2 plus O2 minus, Mg2 plus CO3 2 minus. Okay, and it will give you CO2 gas. That will be a solid. You're heating this solid and then lose CO2 gas. When you lose CO2 gas, you are losing mass. You are losing mass of the CO2 that escape as a gas. So if you hit 100 gram of this, you will not get 100 gram of this because you lost mass. Conservation of mass. Whatever mass you put in here must be equal to the total mass here. But you lost this as a gas, you lost CO2 as a gas. So what happened is you get a decrease in mass, and therefore this is called gravimetric analysis, because you need a mass balance. You need an electronic mass balance that can measure mass, that can tell you the mass of what you started with, mass of what you end up with after you hit it strongly. And how can you ensure, how can you make certain that all the magnesium carbonate has already decomposed? That means when no more CO2 is given out, that means there's no more change in mass. If there's no more change in mass, then whatever mass that you measure at the end of the reaction after heating, it will be constant. That's what is meant by heat to constant mass. When you heat to constant mass, there's no further change in mass because no more CO2 is being lost, and therefore we are certain that all of this will have decomposed when there's no further change in mass. That's why we heat to constant mass. Alright? So something which is often asked not just in A-level paper 3, not just in A-level paper 5 to do experimental planning and design. It could also be an analysis and evaluation question in paper 5 for A-levels. They give you the results, they ask you to think about the procedure. It could of course also be an O-level or IGCSE alternative to practical kind of question, because it requires you to think about the thermal decomposition which you learn, to think about the change in the mass which you learn, reacting masses, and also balancing question. So looking at this individual magnesium carbonate, so what happened here is magnesium hydroxide does not decompose, magnesium carbonate decompose, but I have 3 lots of it. So when I have 3 lots of it, I'll just add 3, 3, 3. So what I have is 3 magnesium oxide, 3 CO2. But what else does not change? The magnesium hydroxide does not change. So this is what we will see. Alright, this is what we will see. We don't see a colorless gas, okay, but we have a decrease in mass because this would have condensed at the upper part of the tube, which of course if you heat strongly you will get rid of all the water crystallization as well. And then because this escapes as a gas, so the mass that is being left, will be this. So initially you have mass of tube plus solid, mass of tube and the solid before heating, and then you have mass of tube plus solid after heating. So you need to ensure heat until constant mass, and that was exactly what I said just now. When you heat until constant mass, no further change in mass means no further loss of CO2, and all the H2O will have been driven out, because when you heat it, remember in my water crystallization video, when you heat something which is hydrated, the water vapor form on the upper part of the tube, that's where they condense. You really need to heat them strongly to remove all the water crystallization as well, if you want to ensure that you are only measuring the mass of this particular solid that remains. Okay, so that was just an example of another mixture of two compounds there. So it wasn't exactly a salt, because magnesium hydroxide is a hydroxide, is what you call a base, okay, an alkaline solid. Actually, an alkaline is only for solution, so it's a basic solid. So you have a base and a carbonate. This is called a basic carbonate. Okay, basic because it's the adjective for a base, and it's a carbonate, so it's called basic magnesium carbonate. You have here another example of something similar. This is called zinc carbonate basic. Just like I could call magnesium carbonate basic, it's exactly MgCO3, MgOH twice, dot whatever water of crystallization. So here they didn't mention any water crystallization. I can't find any formulas at all. This is a very, very old sample again. But if you look up on the internet what zinc carbonate basic is, it will contain ZnCO3, and then it will have a dot, you will have zinc hydroxide. What I'm not sure, however, is the ratio of how much zinc carbonate there is to zinc hydroxide, because it's a mixture, right? Mixture is not a compound, and mixture means, since it is not a compound, the things that you are mixing together does not need to be in a fixed ratio, whereas a compound consists of two or more elements combined chemically in a fixed ratio. Like when you have H2O, water, steam, ice, H2O, the hydrogen to oxygen is 2:1 ratio. 2 hydrogen is to 1 oxygen. Every time you have water or ice or steam, you must have 2:1 ratio, unlike mixture. So this is also a white solid. Okay, so zinc carbonate, zinc 2+, Zn2+. This will make sense to you if you are doing A-level chemistry. Even though zinc is in the transition metal series, why does zinc 2+ does not form colored compounds? Okay, so these are a very popular A-level question, and that is to do with something called electronic configuration. Not the simple one you learn in O-level and IGCSE, but the more complicated one that you learn in A-levels. So you can imagine the definition. So you should be able to define what is a transition metal based on A-level standards, and then you work out the electronic configuration of Zn2+, and then it will make sense why the compound of Zn2+ are not colored. Okay, so that was just for the reference of A-level students, ready? Okay, so time to get started on the experimental procedures, which is what I really want to convey for these particular tutorials. Okay, so let me get started. I want to move my iPad away from all this fire and stuff. Okay, so we have an array of test tubes here. So let's focus on my face and more focus on the practical itself. What do I have? Okay, so I should take out some solid. Let me start out with something simple, which is aluminium ammonium sulfate. Clean spatula. So in the real deal, yeah, you might be just given the solution, or you could be given the solid, alright? I want to start from the solid because I want to show you the water crystallization effect. Okay, so this is a white solid. This is a dry test tube. If it is not dry, it will have stuck on the side, obviously. So this is a dry solid. It's very, very crystalline. It's a white solid. It's ammonium aluminium sulfate. It's hydrated. Okay. So I have a Bunsen burner here. Test tube holder. So make sure your test tube holder is tight, because I think I broke one accidentally because the test tube holder was not tight enough. Yeah. So make sure that when you start the Bunsen burner, the air hole is closed, because you don't want to not be able to see the flame at all. Okay. Okay. There's gas. I just want to try thermal decomposition first. but then later on we will test for the cations in a separate experiment. Okay, so I'm just heating the solid, just like I did in the other tutorial videos. We will see colorless liquid form on the upper part of the tube. I'll bring it close to the camera so you can see it in a little bit. So I'm heating it strongly. By right, I should be heating in a boiling tube because boiling tube is meant for heating. But yeah, I'm just heating it in a test tube, so I don't want to be heating it too strongly. So how you can see, there is condensation on the upper part of the tube. It is a colorless liquid, so you don't see water, by the way. You see colorless liquid form on the upper part of the tube. So it is actually pretty hot, so you don't want to be touching this end. You do not put it into water straight away, because hot test tubes, hot boiling tube, straight into water, not good at all. They will break. Okay, so colorless liquid form on the upper part of the tube. You can be sure that this thing is hydrated. Well, it was hydrated. You can, of course, heat it until constant mass. That means you also need to heat this region with the water of crystallization in order to drive off all the water of crystallization. How can you ensure that the compound is anhydrous? Well, you need to heat until there's no more water vapor on the side of the test tubes. I don't want to be doing that because I got a sticker on the side there. You need to be heating the solid until there is constant mass. So you need the mass of the test tube and the solid before you heat it, and then you need the mass of the test tube with the solid after you heat it, after you get rid of all the water crystallization. Put it on top of the mass balance. But this is a test tube, it can roll. So what happens is you can use a beaker and put it in a beaker. So it's a beaker plus the test tube with the solid before heating, and then the beaker to support the test tube, plus the solid after you heat it, and that has to be to constant mass. Okay, so after I dry out the water crystallization, it does not matter anyway. Ideally speaking, okay, they could really ask you the thermal decomposition or driving off the water crystallization for each and every one of these hydrated salts, but that is actually not the focus of my tutorial in this video. So I will not heat any more substance now, because I just want to test for cations. Okay, so I want to test for the cations, potentially the anion as well, for these experiments, and there is the majority of, well, there is the main objective of this tutorial. Okay, so I just want to show you that they're hydrated and that they can give off water crystallization. Yeah. So in order to test for cations and anions, so usually I would dissolve the thing in solution. This was what I just heated, and even though I drive off the water, when I make up the solution, I will add something called distilled or deionized water. So we never ever use tap water to dissolve our solution for qualitative analysis, and that is because tap water contains dissolved ions, and distilled water, which is also called deionized water, does not contain any dissolved ions at all. Right? So I do not want to be adding cold water straight to the hot test tube. I'll just measure out a new test tubes of this aluminium and ammonium. Aluminium and ammonium, right? That's what they say. Aluminium and ammonium sulfate. So there is the solution there. I'll add some water. In fact, I want to do a couple of tests because I want to ensure that, you know, I want to do quite a lot of tests. So I'll probably dissolve it in a larger amount of water, because I will separate this into different portions and do different tests. Okay. Just want to ensure that I've got enough. So all ammonium salt will be soluble, but not all aluminium salts are soluble, obviously. Okay, but I think this one should be all soluble in water. Just need to make sure that they are soluble. Put the spatula aside because I don't want to contaminate anything at all. So I did say I wasn't going to heat anything anymore, but I do still need to heat it. So this thing, in instruction, they will usually ask you to separate into however many portions. So I'm going to test for several things. So this is aluminium ammonium sulfate. Oops, I don't want that too much. That's alright. So first of all, when you test for anion, there are a couple of things you can do to test for anions. So in the qualitative analysis notes, if you are just given colorless solution, how can you test for anions? Well, to test for the anions, most likely is sulfate, nitrate, chloride, bromide, iodide, carbonate. Okay, if you really don't know what it is, then you need to add acid to it. Okay, you need to add acid to it. Maybe I'll just separate into different portion again. So we need to do quite a lot of tests here, because if you don't know what it is, you need to do quite a lot of tests. If you don't know what it is, okay? We of course we know what it is. So I just want to show you roughly what it means. If it contains carbonate, then when you add acid to it, acid such as, we'll bring this over here. So when you have acid, you can add dilute nitric acid, or dilute hydrochloric acid, or dilute sulfuric acid. Any acid, when you add it to nitric acid, to anything that contains carbonate, it should effervescence. But there is no effervescence at all here. When I add nitric acid to this solution, there was no effervescence. It tells me that there is no carbonate. There is no carbonate. Okay. If there is no carbonate, can there be a halite such as chloride, bromide, or iodide? This solution is colorless. It tells me that there are no transition metal cations, but of course some color complexes are very difficult to see because they are mixture or they're very dilute. Okay, so you cannot, obviously something which is colored very obviously tell you there's transition metal present, but then sometimes it's difficult to see because of concentration, because of other things behind it as well as a mixture. Yeah. So we are sure there was no carbonate. There's no CO3 2- because there was no effervescence when I added acid to this colorless solution. Remember, we knew what the solid was. We knew what the solution contained. But I just want to show you that it gives negative result with the other ions that we are testing. Carbonate down. So after I added some nitric acid and there is no effervescence, no carbonate, with the nitric acid in there, so that's why they say acidify with some dilute nitric acid, or acidify with, yeah, you can only use nitric acid. Acidify with nitric acid, then you add silver nitrate. This is aqueous silver nitrate. It's not very clear now. It's always contained in a dark container because silver 1 or silver plus 1s, and then nitrate, silver 1 nitrate, very sensitive to light. They give you that silver ions. So silver nitrate is used to test for halite. So with the nitric acid in there, acidify with nitric acid, then add silver nitrate. You see there is no precipitate. Silver chloride is a white precipitate. Silver bromide is a cream precipitate, and silver iodide is a yellow precipitate. You can still see my hand through it. It is not a precipitate at all. Don't know why it's a bit cloudy, but it is not a precipitate. When you get a silver chloride, silver bromide, or silver iodide, it is very clear there's silver chloride or silver bromide or silver iodide, because there will be a precipitate which is very clear. So with the acidified solution with nitric acid, I ensure there was no carbonate. Then I add some silver nitrate, and there was no precipitate, so there's no chloride, bromide, or iodide. Okay, and then because this one is regular silver nitrate in there, I don't want to use it anymore. So this is another portion. If I want to test for other anions like nitrate, NO3 minus, then I need to add sodium hydroxide. When I add sodium hydroxide and I add aluminium foil, do I get ammonia gas or not? However, this is tricky because remember what this was? This was ammonium aluminium. Ammonium aluminium sulfate. So it contains ammonium ions. Even without the aluminium foil, ammonium ions is NH4+. When you add sodium hydroxide, which is NaOH, when you add sodium hydroxide to something that contains ammonium ion, and then you heat it, you will get ammonia gas that will turn red lemons paper blue. Okay, and there's something I'll do later on. So I will not test for nitrate here. until you test for ammonium first. Because in my other tutorial video on qualitative analysis, there's a compound called ammonium nitrate. Ammonium ion has a different test to testing for nitrate ion, but both of them will give you NH3 in their test. These are something that you will have learned from your O-level or GCSE or IGCSE practical, something that you revisit in A-level qualitative analysis, something that you must be able to differentiate that the NH3 come from different sources, NH4 plus as well as NO3 minus. The test for NO3 minus require you to heat in the presence of aluminium foil. Okay, so you can watch that tutorial video. So I'm not going to test for nitrate here, okay, but I just briefly outlined what was the problem, right? And the other ion that I'm testing for is sulfate. So I'll use something called barium nitrate. This is Ba2 plus NO3 minus twice, because plus 2 must be balanced by minus 2. So I need 2 of the nitrate. Barium nitrate is Ba2 plus NO3 minus twice. Sometimes we use barium chloride. Colorless solution, this was aluminium ammonium sulfate. But remember, when you test for something, you're trying to find the identity of the cations and anions, so you don't really know the identity. Okay, so let's see what happened. What do you see? Now you have a white precipitate. This is very clearly a precipitate. You cannot see my hand behind me. You cannot see my eye behind, well, one of my eyes. Okay, so that means this is a white precipitate. It's a white precipitate when I add barium nitrate or when I add barium chloride, so BaCl2 aqueous, which is colorless, or barium nitrate, which is colorless, because all nitrate salts are soluble in water, and I get a white precipitate. This tells me that sulfate is present. SO4 2 minus is present. So there's my anion. SO4 2 minus is present. Of course, you could also test for other anions because this is a mixed salt, but we knew originally it was ammonium, aluminium, or aluminium ammonium sulfate. So the anion there is just sulfate. Okay, so the next bit will be testing for cations. Testing for cations. In your test for cations, you would know that you have a table where you have adding sodium hydroxide and then adding ammonia. Okay, so that is exactly what we're going to do. So I've got more portion of the solution that I need, but anyway. So when I add sodium hydroxide, so this is my solution, okay, another portion of that solution. So I want to add sodium hydroxide. When you first add sodium hydroxide, you want to add them liter by liter because you want to see what happened. So this is lesser than 1 cm3. 1 cm3 is around there. So typically when you add at first, before you add in excess, you need to add the same volume. So if I use lesser volume, then I'll add up to there, which is almost double the volume. If I use 1 cm3 here, then I will add up to there, which is almost 2 cm3. Okay, so it depends on how much you have in your test tube. Do you see anything? Not much really. Am I supposed to see something? I don't know, they are probably not too concentrated. So we know the ammonium, we know the ammonium ions. Ammonium ions are soluble in sodium hydroxide, but I know aluminium. I know aluminium is not soluble, so this thing is not very clear. I wonder why. I think my stuff is not concentrated enough. Let me try this. Yeah, it's very faint actually. So the fact that I knew there was Al3 plus in there means I'm really sure there should be a precipitate. So I need to try and get a lot more of the solid. So that's why, like in Cambridge exams, they have this instruction for examiners. We need to make up the solution to a particular concentration, because when I don't have a lot of the solid, that means I have very low concentration. Sometimes you don't see it. Okay, so that's why, like as center supervisors, like we all need to be careful in order to really prepare the solution according to Cambridge standards. Okay, because Cambridge knows at what concentrations they will give you the result. So just now, even though it contains aluminium ions, they are not very visible. So I'm trying to dissolve a lot more of the solid to try and get a lot more concentrated solution. So I'm preparing the solution from scratch, right? So I'm not like making a stock solution like what Cambridge asked me to do. That's usually what the lab tech will provide for you. So this thing now is not very soluble in water. So I've just dissolved more of the ammonium, aluminium sulfate in water. Okay, because I want to try and show you, they're supposed to precipitate out with sodium hydroxide, but just now it was not clear at all. So my suspicion is that my solution was not very concentrated, and that's why it's very difficult to see the precipitate. So I'll let the solid to settle down, and then I will take out a little bit of it for my test. Just use a clean dropping pipette. So at the moment you see the solution is a bit cloudy-ish, but there's a very fine solid that's settled at the bottom. So not very soluble at all. But I think it should prove my point. Okay, so suppose I have this thing, so it is reasonably clear to start with. When I add sodium hydroxide, I have aluminium 3+, remember? I also have ammonium ion NH4+. NH4+ with sodium hydroxide on its own will not do anything until I heat it. Then I will get ammonia gas, which is the test for ammonium ion. Okay, but I also have Al3+. When I add sodium hydroxide, I hope this will be positive. Do you see how the precipitate comes out? So it's much clearer here compared to just now. So I started with a clearer solution, but now the solution is a lot cloudy. So it is very difficult. You see, Al3+ is very difficult to see when they form hydroxide. So again, it looks like clear thing, but there is a little bit of solid floating around. I wonder if I have a lot more of the solution, will it help or not? I have just put in a little bit of that concentrated solution containing the aluminium ions, and you can see that the precipitate is a lot clearer. So this is exactly what I said just now. Cambridge will instruct the centers, the supervisors, to prepare the solution to a particular concentration, because at very low concentration, Al3+, when they form precipitate with sodium hydroxide, it's very faint, it's very hard to see, because aluminium hydroxide Al3+ with OH-, they will form Al(OH) 3 times. Aluminium hydroxide is insoluble in water. Okay. Oh no, my hand got a bit of hydroxide in there. Anyway, so aluminium hydroxide is insoluble in a little bit of sodium hydroxide. But see what happened when I add in excess. So this one is a lot of white precipitate because I just added a lot of the concentrated stuff. So my feeling is I need to add quite a lot of sodium hydroxide in order to dissolve this. Do you see how the precipitate actually goes away? So now it becomes clear again. You can see through. I hope you can see that it is clear. You can see my hand behind it. Yeah, okay. So aluminium 3+ give you a hydroxide which is soluble. So let me just show you on the screen, it's a lot easier. So aluminium 3+ will give you aluminium hydroxide in the presence of hydroxide. So this is aqueous aluminium 3+ plus 3OH- aqueous, giving you AlOH 3 times. So this is a solid, this is a white precipitate, but then in excess NaOH, this is actually part of what makes aluminium oxide, not hydroxide, aluminium oxide amphoteric, is because this thing can react with excess hydroxide. So this is a solid, this is aqueous, and we saw that it dissolved, right? What does it dissolve into? It will give you 4 hydroxide. Aluminium with 3 hydroxide, the charges balance out. So now with 4 hydroxide, the charges do not balance out. and then with 4 hydroxide, the charges do not balance out. So what happened then is you have an overall minus charge there. Okay. Oh no, I didn't record the thing there. Okay, never mind. I better just show you on the screen there. Okay, so I was going to record the thing, but I forgot to record it. So aluminium hydroxide, and then there's the aluminium 3 plus with 4 OH minus. So you get the Al OH4 with the minus charge there. Okay, so that thing there, the last one, is going to be aqueous because it is soluble again. Okay. Anyway, so I should test for the other cations. So I added excess sodium hydroxide just now, right? And then I get a clear solution. So this is in excess sodium hydroxide. I should test for the ammonium ions, because when you add excess sodium hydroxide, you should test for ammonium ions always. If they tell you that there is another ion present, and if it is not colored, you should always keep an eye out for ammonium ions. Test for ammonium ions is not that difficult, but you need to know what to test for. So what happened then is, well, let's light up. So blue flame. My red litmus paper, I should moisten it with a little bit of distilled water so that it's wet. Okay. Remember, you're testing for the gas, therefore do not insert this into the side of the test tube which contains sodium hydroxide. So heat it. This is actually quite a lot of solution, so it's actually a bit dangerous to heat that much, but I will try to be careful. So in the presence of sodium hydroxide together with ammonium ions, so what happened then is they will give off ammonia gas. Hopefully, they should. So I will try and heat this. And then usually you'll be able to smell. Okay, if you can smell a pungent gas, P-U-N-G-E-N-T, coming out from the... This is a lot of solution to heat actually, so that's why it's taking so long. I will remove some bit of solution so that I am not heating that much, so that it won't take that long. Perhaps I need a bit of stronger fire. Okay, starting to heat up now. I'm just waiting for the gas to be produced in a bigger amount before I bring it close to the camera so that you can see what is happening. So it is starting to boil. There is a gas coming out. So my moist red litmus paper has turned blue. My moist red litmus paper has turned blue. So by heating the solution, and of course you can whiff it as well. It is ammonia, right? You know, it smells like a lot of urine accumulated in the toilet. So my red litmus paper has turned blue. So my observation is, in the presence of excess ammonia, I get a colorless solution, so the white precipitate dissolve. When I heat it, that solution that contains excess sodium hydroxide, I get a gas, I get a pungent gas. The pungent gas turns red litmus paper blue, okay? And therefore the gas is ammonia. If the gas is ammonia, the solution that I heated in the presence of excess sodium hydroxide must contain ammonia. Must contain ammonium ions. So what I'll do is, let me just do this on the screen so that it's easy. Remember that I have a mix, I have a double salt. So I also have NH4+. That reacts with hydroxide, but it needs a bit of energy to kickstart the reaction. This is called activation energy. So when you heat it, it will give you NH3 and it will give you H2O. This is the gas that you get. This is the gas that turns red litmus paper blue. In fact, it turns moist or damp red litmus paper blue. This is aqueous, this is aqueous. this is a common ionic equation to show the production of ammonia when you have any hydroxide, calcium hydroxide, sodium hydroxide, potassium hydroxide with ammonium ions, any sort of ammonium ions, whether you have ammonium compound as one compound or when you have ammonium compounds as a double salt, it still contains ammonium ions, right? So it will give you ammonia when you test for ammonium ions. Alright, so moving on to the next bit, I think the next tutorial that I'll show you is to do with one of these double salts. Okay? So it's also double salt, but I'll just spend the rest of this tutorial focusing on ammonium ion 2 as well as ammonium ion 3. Okay? So I am testing for ammonium, so I must make sure that I have enough red litmus paper. Alright, so let's get started. So I won't do the heating bit of the solid again because I already shown you enough on water crystallization. So I'll just scoop out ammonium ion 2 sulfate first. So clean spatula. I think this one hasn't been used for a long time. Okay. So ammonium ion 2 sulfate is not a common thing in all level obviously, but mixture is a common thing, and then formula of ammonium sulfate, formula of ion 2 sulfate is a common thing, and of course qualitative analysis is just observation, so they could potentially ask you anything they want. Alright, so I think I dissolved enough of the solid. I think should be alright. Okay. So this is ammonium ion 2 sulfate. Ammonium ion 2 sulfate. I'm going to make a solution of this. This is in water. So it's meant to be a bit pale green in water, but I think the sample is really old, so I'm not sure whether it will work or not. I'm sure the majority of it is still ion 2, but as you know, ion 2 can get oxidized to ion 3. As a solid, I don't think it's that quickly, but I've got a solution, so it's a bit colored, but again, color like this is very difficult. It's supposed to be a clear solution. All ammonium salts are soluble in water. I will test for the anion very quickly because we know that it is a sulfate, so I won't go and look for other anions now because my focus will be on the sulfate, where I use barium nitrate or barium chloride. Okay, so they will do the same thing. This is almost a clear solution, so it's a bit colored. Okay, what happened? You get a precipitate. You get a white color precipitate. Sometimes the white color is not that clear because remember you have the presence of a transition metal compound, and even though the transition metal compound does not react with barium nitrate, but then in the presence of other colors it can be difficult to see the color that you want to see, but this is very clearly a precipitate. And if you get a precipitate with barium nitrate, it must be a white precipitate, and that white precipitate is an indication of barium sulfate being formed. Alright, so you can write a equation for it, and you have to know how to write the equation for it because it's a classic precipitation reaction. So this is a classic precipitation reaction. We are adding barium 2 plus to something that contains sulfate, so you get barium sulfate, which is a solid. This is aqueous and aqueous. Okay, this is a white precipitate, and that was exactly what we got, and we were just testing for the sulfate. And now we need to test for the ion 2 plus as well as the NH4 plus. For this ion 2 plus is a cation, and because it is a cation, so what we do is we need to use we can use ammonia. We can also use sodium hydroxide. In fact, I'll show you the result with both sodium hydroxide and ammonia. So realistically speaking, I need to divide it into another portion so that so that we can test with ammonia. So usually you'll be given a lot more solution than this. This is actually lesser than 1 cm cube. 1 cm cube is around that much, so I'm just using half the volume, which usually you will use a bit more. But when you have a lot more of the solution, the test tubes, you will need a lot more of it for it to have an equal amount before you add in excess, right? So let's try ammonia first, okay? Let's try sodium hydroxide first, okay? So this is the ammonium iron 2, ammonium iron 2 sulfate. We already confirmed the sulfate. This is a sodium hydroxide. I'm just adding this thing there. Oh, this is good, okay, because it's still green, okay. How we can see is a dirty green precipitate. So I'm wearing a dirty, well, this is kind of green t-shirt, I guess. So it's pretty much the same kind of color as my t-shirt, so don't worry about Sully in the background. But anyway, so it looks pretty much like the color of my t-shirt. I wasn't planning on this, but anyway, if you cannot see color very well, get a white background, use a white tile or something. So I've just purposely shake it on the side. I want you to see roughly what happened on the side. Okay, this was in sodium hydroxide, so you get a precipitate because you cannot see through. You get a yellow, well, not yellow, sorry, you get a green precipitate. But in your qualitative analysis, you know that green precipitate could also mean the presence of chromium 3, because chromium 3 hydroxide is also a green precipitate. That's why we need to add excess sodium hydroxide to make sure what is going on. Okay, so what I'm going to do now is I get a green precipitate. So I added almost equal amount, right? So I'm going to add excess now. Adding excess, I see what happened. Do you get a precipitate? Yes, the precipitate remains, because as you can see, you cannot see one part of my eye because this is not a solution. You can shake. This is not a solution. It is not see-through because this is a precipitate. So you get a dirty green precipitate, which is insoluble in excess. So when you have iron 2 plus, we add aqueous NaOH. So we get, well, actually this is what you write in your column, a dirty green, or you say green, that would have been alright. Precipitate is formed, but that is not enough, because as I said, it could also represent chromium 3 hydroxide. That's why we need to add in excess, but then it is insoluble. So the precipitate is insoluble in excess. So maybe I should write the precipitate, because it could have been in another box, alright? The precipitate is insoluble in excess aqueous NaOH, or you can write NaOH aqueous. Okay, so this confirms, therefore, iron 2 plus is present. On its own, if you just say a dirty green precipitate is formed, it does not confirm iron 2 plus is present until you mention the result of what happened when you add an excess. Okay, there's actually another observation that you are supposed to take note of. This is usually not stated in the table, or usually not what is stated in the theory, unless you actually do the practical and you can see it. Okay, I want you to see very carefully what happened on the upper part of the tube. Alright, so in the presence of excess hydroxide, a little bit of the iron 2 hydroxide on top is supposed to get oxidized. I think I mentioned in my other qualitative analysis video. You see the upper part of the tube here? You see they're a bit reddish brown, and that was because I swirl around the iron 2 hydroxide onto the side. And the iron 2 hydroxide, in the presence of more hydroxide, in the presence of oxygen in the atmosphere, iron 2 hydroxides get oxidized. Oxidation, iron 2 become iron 3. So you get this iron 3 hydroxide, which is a reddish brown PPT, as we will see later on when I did the qualitative, when I'm going to do the qualitative analysis on ammonium iron 3 hydroxide. Okay, so just to finish off, I want to test for the cation as well, because they can provide this scenario as a mystery to you, something to investigate. They say it contains another colorless cation, another cation which produces colorless solution, and how do you test for it? Well, in the presence of sodium hydroxide, when you get a green color precipitate, can you tell calcium is present? You cannot, because calcium hydroxide, aluminium hydroxide, zinc hydroxide, those are all white precipitate. And if they are white precipitate, then it's very hard to see the color in the background of these colored compounds, alright? So that's why it's difficult to identify those cations, but it's easy to identify ammonium cations. So I'm just going to heat it. So back to Bunsen burner. Make sure the air hole is closed. Just want to prepare my red litmus paper so that I can test for my ammonium ions. I want to moisten it with some distilled water. And we are ready. So something that contains ammonium ions, okay, and then in the presence of sodium hydroxide, when I heat it, I will get a pungent gas, P-U-N-G-E-N-T. You heat it until it doesn't exactly boil, but it reaches the kind of boiling point, because Bunsen burner heat is actually very intense when it's on blue flame, okay, not when it's on yellow flame, okay. So you never heat with the yellow flame. It's starting to boil already. I get a bit of gas given out already. Okay, the gas is given out. Oh no! Okay, I better heat it a bit more. It's not very clear. Oops. Okay, that's why we need to actually heat it in a boiling tube, because a boiling tube is deeper in depth, and boiling tube can store more volume. So we can see the red litmus paper has turned blue there. I didn't put the red litmus paper inside because it's got sodium hydroxide on the side of the test tube. So I'm just testing for the gas. Alright? Be careful with fire, yeah? So there's the number one danger in the lab. So I already spilled some stuff here, so I need to wipe them up before I continue any further. Very dangerous when you have spillage in the lab, especially when I've got electronic devices, because I do not want to damage my electronic devices for obvious reasons, okay? Okay, never mind. So all that is done. I'm just left with the last thing that I need to show you. Well, that I want to show you. I don't need to show you. This is ammonium ion 3. This is different, right? Just now was ammonium ion 2. This is ammonium ion 3. The solid looks white, but that's because it's a mixture. Okay? So of course it's hydrated, but I'm not going to show you the heating bit about the water crystallization. Those were already covered in the other tutorial videos. What I'll show you, however, is a qualitative analysis of a double salt. So this compound is kind of soluble in water, but not very soluble in water. So I might just try and dissolve it as much as I can, and then I might just take the solution out, because I do not want to be testing the solid, I want to test the solution. So I might need to add a bit more water to dissolve it actually. Just like sugar, right? Sometimes you need a bit of heat to dissolve stuff. So I will let it settle for a bit, and then I will separate them out into the things, okay? I do not want to use the sand dropping pipette because I used it for my Al3+ ion just now. It's starting to settle. First portion, I'll test for the anion, which already I knew was sulfate, so obviously it's just the barium nitrate test or barium chloride test. Second portion, I'll test with ammonia, just to show you that we can. And the third portion, I'll test with sodium hydroxide, okay, to test for the cations. So this one is the solution. So this is iron 3+ solution in water. Be careful, yeah. A lot of students, they are always confused, okay? If you look at this is iron 3+ aqueous, alright? So now we have iron 3 plus aqueous. We also have NH4 plus aqueous. We also have SO4 2 minus aqueous. Alright, so when you have iron 3 plus aqueous, there is no hydroxide. This is a solution. This is not a reddish brown precipitate. Why? Because this is in aqueous. Aqueous means in water, not OH minus. Okay? So what happened then is Fe3 plus aqueous is a yellow orangey kind of solution. Iron 2 plus aqueous is supposed to be a pale green kind of solution. You don't do a lot of transition metal chemistry in O-level or IGCSE, but this is actually very important in A-level chemistry. Okay, a lot of students, they get confused between what is solution and what is precipitate. Without the OH minus, there is no reddish brown PPT. Okay, iron 2 plus is a green, very pale green solution in water, but then in the presence of hydroxide, it gives you a dirty green precipitate, which you saw like 5 minutes ago, and then it dissolves. It's insoluble in excess ammonia. It's insoluble in excess sodium hydroxide as well. Okay, so what I'm going to do is I will add barium nitrate. Where's my barium nitrate? Barium nitrate. Okay, this is to test for the sulfate. So clear solution. As you can see, it form a precipitate, which of course, what would people say? Alright, okay, this is a very tricky one because the solution was very clearly brownish, so the precipitate looks a bit brownish. So do you say a white precipitate or do you say a brown precipitate? Okay, unlike the previous one where the solution was very light to begin with, almost not colored, so it was very clear just now it was a white precipitate, but here the solution was a bit orangey to begin with, and now you get a precipitate. That precipitate looks a bit orangey because of the presence of the iron 3 plus in solution, Fe3 plus aqueous, which was not a precipitate. It was, again, I specify, I emphasize, it was iron 3 plus aqueous. It was light yellowy, kind of orangey brown. Okay, but it was a solution. All right. Now the color here was the precipitate of barium sulfate. I show you the precipitation reaction earlier. Ba2 plus SO4 2 minus give you BaSO4. We know that one is a white precipitate. So when we add barium nitrate to it, we saw like a off-white because here there is a bit of browning, but essentially it still tells you sulfate is present, and you know it should be white, but because of the interference from the brown color, the orangey, yellowy color of the iron 3 plus in solution, that's why you see a little bit of browning there, but it confirms the sulfate is present. Yeah. Now to the other portion, this is also the solution, the clean portion. I'll add ammonia. What happened when I add ammonia? I just remember I didn't add ammonia to iron 2, but it's going to be the same result as sodium hydroxide actually. So I add ammonia. What happened to the solution? Do you see that it starts to become cloudy? That's because a precipitate has started to form. Just now it was a solution. Now you cannot see through already. Now you cannot see through it because it has formed a precipitate. So be careful what is a solution and what is a precipitate. You cannot see through anymore. You cannot see through me anymore because you get a looks like a reddish brown. Okay, reddish brown PPT, and this is with iron 3. Okay. Now, this is what happens when you add a few drops. What happens when you add excess ammonia? This is still a precipitate because even though it looks like it has dissolved, can you see through it? If you cannot see through it, you cannot see me, right? That means it's a precipitate. You do not say it dissolved because you cannot see through it. Like just now, the aluminium hydroxide was a white precipitate. In excess sodium hydroxide, you could see through it because it went colorless, right? Just like this, it does not go clear. Yes, it's colored, so it doesn't go colorless, but you do not see through it in excess ammonia. Okay, that is because the iron 3 hydroxide is insoluble. Okay, so when I add ammonia, I get a reddish brown PPT, or you can say orangey brown PPT is formed. the PPT is insoluble in excess. Okay, insoluble in excess NH3, because that was what I added. I added NH3, which was aqueous ammonia. Okay, so it confirms iron 3 plus. But that is just one of the tests that is possible for iron 3 plus. The second test, of course, is add NaOH, and we'll get similar kind of results. So this is a clean portion of the solution, and we will add sodium hydroxide. So clear solution. So this is clear, is see-through. Now you cannot see through. Okay, it started to precipitate out. Just now was iron 3 plus aqueous with no hydroxide. Now this is iron 3 hydroxide. Okay, this iron 3 hydroxide which precipitate out, right? Like the dirty green precipitate, this is a hydroxide precipitate. It's not a see-through. It looks like it is a see-through, but it is not a see-through, okay? Oops. Don't know how clear it is, but you can't see through it, okay? If I have the word behind, can you see the word behind it? If you cannot read the word behind, that means it's not a see-through, alright? So this is an orangey, reddish brown kind of precipitate. Okay, so it is exactly, share my screen here, but anyway, paste. Okay, but of course it's not going to be NH3, it's NaOH aqueous. I'm just going to add excess sodium hydroxide, which I already shown you on the screen. It will be insoluble as well. It looks like it is a see-through, but I hope you can see. I don't know how clear it is. There's like little bits and pieces inside. It's like suspension. So it's not a clear solution. Because it's not a clear solution, so the precipitate does not dissolve in excess NaOH, okay? So I'm not too sure how clear it is, but it's like a suspension of the precipitate inside the solution. So it looks like it is dissolving, but it is not dissolving at all, okay? There you go, you see like a suspension of solid inside, okay? So the precipitate is insoluble in excess NaOH. And when I add the excess NaOH, I also need to test for the ammonium ions. So what I'll do is, I will remove most of the solution because I do not want to spill it again. What else? Okay, I ran out of my litmus paper. I already used 2 tests for ammonium ions earlier. But what you do again is, where's my other thing? This thing. You do not heat a test tube that is half full, okay? Because it will spill very easily and it's very dangerous to the person next to you, which of course you won't be like me today because I'm working alone here, but you have other people around you. It's dangerous, and you might even spill it on your question paper, and that is bad because if it is a real exam, you get 1 question paper per person. You do not want to spill anything on your question paper, alright? So be very careful. Never ever hit a test tube that is like more than a quarter full, okay? Throw away some of the solution. After you add in excess NaOH, swirl it, and then throw away some of the solution before you heat it in the test tube. Unless you transfer it to a boiling tube and then you can heat it more intensely, alright? But you can heat a test tube, just be very careful, it's for a small volume. I'm not going to heat it for ammonium ion here because like I said, I ran out of my red litmus paper. So I'll leave it here for today. But essentially you should, turn on the Bunsen burner, heat it, get a gas, and then you have moist red litmus paper or the moist red litmus paper. Sorry, did I say moist twice? Moist or the damp, DAMP. You damp it or you moisten it with distilled water. You test for the gas. You get a pungent gas that turns red litmus paper blue. The gas is ammonia, NH3. Therefore, this thing contains NH4+. Alright, so I'll leave it here for today in this tutorial at least. But what have I covered today? I talked specifically in this tutorial about double salt. Double salt meaning 2 different salts such as ammonium sulfate mixed with iron 2 sulfate. or it can be ammonium sulfate mixed with iron 3 sulfate, or it could be one of those white color solid which is not a double salt but it's a carbonate, zinc carbonate plus zinc hydroxide as a mixture, or even magnesium carbonate as and also magnesium hydroxide as a mixture. So the magnesium carbonate or zinc carbonate basic, they are typically part of gravimetric analysis, which is to do with thermal decomposition or recording masses in terms of reacting masses and loss of mass of CO2, whereas these things are usually part of it could be a redox reaction actually, because the iron 2 can undergo redox reactions, and they could ask you what is the percentage of iron 2 in here, and you could do a redox titration with an oxidizing agent to oxidize the iron 2, which will not touch the ammonium ion. So if you know how much mass you use, okay, then you know how much of KMnO4 titration, therefore you know how much iron 2 plus, and therefore you know how much iron 2 plus is in here. Then you can work out the mass of the iron 2 sulfate in here. Then you can work out the percentage of iron 2 sulfate out of the whole mixture. So there you go, there's another titration question. It's a very common backward titration question. You can catch out my backward titration topical playlist under AS moles and stoichiometry. They are usually more advanced than O-level or IGCSE standard, but if you are keen, you can check out those backward titration topical playlists under AS stoichiometry and mole concept. Okay, so I briefly went through qualitative analysis of how we look for anions, but I did not extensively did everything. Okay, but when you are just given a solution and you want to test for anion, you need to test for carbonate by adding acid, whether you get effervescence or not. You need to test for halite, chloride, bromide, iodide, by adding silver nitrate, because silver chloride, silver bromide, silver iodide, they are all precipitate. You need to test for nitrate, NO3 minus, by adding aluminium foil in the presence of sodium hydroxide, and then you heat it, and then you get ammonia gas. But of course, we have ammonium ion. So how can we be sure that the ammonia gas does not come from ammonium ions? Those are things that I cover in my other tutorial videos on the qualitative analysis involving ammonium salt. Okay, so you can catch that that particular tutorial video. And towards the end, I also test for both the colored cations, the cations that come from colored species. There's the iron 2 and iron 3. So it's very hard to see any white precipitate against the colored precipitate background, but because it's ammonium ions in the presence of excess sodium hydroxide, we can heat it, and then we test with moist or damp red lemon pepper. That will confirm the identity of the ammonia gas, which will then confirm that ammonium ion, NH4+, was present in those original solid, which is present as a mixture. Double salt is a mixture. Okay, that's it for me in this experimental tutorial video. I think that has gone long enough. Do let me know if that has been useful, and I don't know, I've spoken about a lot of things. They could be spread out across different questions, different years, for the practical kind of experiments, for not just O-level IGCSE, but also for A-levels, even part of paper 5 planning, experimental design, analysis and evaluation for the A-level paper. Okay, thank you for watching. Don't forget to subscribe to my channel. Click the button on the bottom right, and do share the channel widely with all your friends, all your chat groups and study groups, your juniors, your seniors, your relative, and whoever else you think might benefit from these tutorial videos that I make on my channel. Okay, so good luck with everything, and look forward to hearing from you. Okay, and follow me at ptet.chemistry, ptet.chemistry, across all the popular social media platforms like Facebook, Instagram, and Twitter, if you are on this social media platform, or once you return to them after you finish your exam. Thank you for watching. I'll see you in the next tutorial video.